All right, so let's begin with a question. If I were to give you a function, okay, say it will be d over dx, and I write down x cubed, what would that give me? Something really straightforward. 3x squared, right? Straightforward, probably don't even have to think about it. If I then change the actual numerator, so I'm going to differentiate this with respect to y now, and say I was to write down the sine of y, okay, so that's what I'm differentiating. What would the answer be? Cosine of y, exactly. Okay, so if you're differentiating a variable with respect to that particular variable, it's not a problem. Before I begin, I just want to say this: if I'm differentiating x, so if I'm differentiating some variable y, which is a function of x, with respect to x, it's actually the same notation just to write this as dy over dx. You're actually just doing the same thing. It's just question notation. Okay, same thing. So that's not a problem. That's where we are so far. That's what we've learned so far. The problem is if I then say work out with respect to x, differentiate with respect to x, differentiate y squared. That part now is a problem. Okay? How do you do that? We don't know what y is. We know y, it probably is some function of x, which we don't know. And you want to differentiate with respect to a different variable x. How are you going to do that? Is there a standard rule? In order to resolve this problem, what we'll do is say let u equal y squared. Okay? And so therefore this problem is essentially saying work out du over dx. That's what the problem is saying, right? And so we know du over dx is just going to be du dx. Okay, and I'll highlight this just to emphasize there's my du dx. So that's what I do. And in between them, I'm going to put my third variable. I'll put y down. And so my answer will be du over dy. Well, I can see what I'm going to get from here. Du over dy will just give me 2y multiplied by some dy over dx. And that will be my answer. That's my final answer. So obviously this is, I'm going through every single step. You normally wouldn't do this once I'll give you the formula, but we're coming on to the formula. But that's how this works. That's how this works. So the implicit differentiation, when you're differentiating something like a y squared with respect to x, the answer would be differentiate the y squared to give you a 2y, and then you get a dy over dx. Okay? Let's take this further. Let's look at another example before we generalize some sort of rule. Say we had to differentiate, I'll change color here. Say we had to differentiate, again, this time with respect to x again, and let's differentiate the sine of y. Okay? Again, we can sort of, over here, if we let u equals sine y, then what we're really asking is work out du over dx. And we know from the chain rule that this must be du dx, and then we put in our third variable, which is a y. And if u is sine y, then u prime, or du over dy, will just give us the cos of y times our dy of dx. Can anyone see a rule emerging? So if I said differentiate, this time without writing all this out, if I said differentiate with respect to x ln of y, without doing all these steps, what would the answer be? what would we get? I'll just open that up to anyone. Go on. 1 over y dy of dx. So if you were to summarize this in a rule, we could just simply say that what we've got, just give me a second, is this. If you're differentiating y as a function of x, you're differentiating some function of y with respect to x, you will get df over dy times this dy of dx, which is sort of just stays there. You don't actually need to work that out normally. Later on you sort of rearrange it, but you just write dy of dx. And the main thing to normally work out is this one here. This is what you work out. Is that okay so far? Any questions? Any questions? Is that clear? Happy so far? Right, what we're now going to do is apply that to different scenarios and see when exactly are you going to use this. Why would you want to do this? What situations? Okay. The first one is obviously let's take a circle. Write down example 1. Say I've got x squared plus y squared equals 25. And I want to find, and the question is, find dy over dx in terms of x and y. So you've got a circle, x squared plus y squared is 25, you're going to find dy of dx. What we could do is simply do d over dx of both sides. I'd write this out just for the first time we're doing it, but I might not do it. I probably wouldn't do it for the other examples. So all I'm doing is differentiating both sides with respect to x. And that means differentiating each term with respect to x. Okay. I'll just write this out for now. Again, I'm probably explicitly putting every single step down, so because it's the first example and you can follow what I'm doing. Right, x squared with respect to x will give us what, David? X squared. 2x, thank you. Here, I've got a y squared. Additive, what would that give us when we differentiate the y squared?
2y dy.
Excellent. 2y dy over dx. Abdul Rashid, when you differentiate the 25, what we're going to get? 0. We can then rearrange this and say, well, dy of dx is just simply equal to minus 2x divided by 2y. The 2's cancel and we get minus x over y. If I was to give you a point, so if I said there's some coordinate 3, 4, so I'd write down at 3, 4, then dy over dx, the gradient at that particular point is simply going to be minus 3 over 4. And so that you can work out the gradient of a circle at a particular point. Is that okay so far? Any questions? Okay. While I'm on this example, I'll just add a little side note to say you might want to, guys, right? You might, if you want to, you could just, as sort of an experiment, rearrange x squared plus y squared equals 25 in terms of just y equals plus or minus. The plus or minus will give you two different equations. When you differentiate them, you therefore get two different gradients. And there's a sense of ambiguity which you'll get if you try and do it that way. So doing the differentiation implicitly helps us to get rid of that ambiguity. So you can have a little play around with that if you want, but obviously doing the implicit, it makes life a lot easier. So you don't need to go down that way of rearranging it, have a plus or minus square root, and then trying to differentiate that. Okay. All right. Let's look at another question. This one slightly harder. What we want to do is show y plus y cubed equals 2 sine x has a turning point at pi over 2, 1. Hands up if you'd like to have a go at it. Hands up if you want me to go through it. Okay, I'll give you a minute. Have a little play around and then we'll go over the answer. So what we've done is differentiated both sides with respect to x. So you've got dy over dx and then 3y squared dy over dx equals 2 cos x. You can then factorize the dy over dx out and then get an expression for dy over dx, substitute pi over 2 for x and y equals 1, and that gives you 0, therefore you know it's a turning point. Okay? Any questions? Yes?
You just have to sub it in, you don't have to actually work it out.
No, because they've given it to you. They've given you that point. So you just sub it in, and that gives you the gradient at that point. The only thing I would say is the term turning point implies it's a maximal minimum, but of course with polynomials you could also get a stationary point, and so a point of inflection. So it's not a maximum minimum, it's not a turning point as such, it's just inflection, it just goes up and down. Alright, let's look at a slightly different example now. And let's look at what happens if you get a product. Okay. What I'll do, actually I could do an example before, just a bit of explanation. Just say I wanted to differentiate x y squared. Say I want to differentiate this. What we could do is just apply the product rule. Okay, so if we call the x part u and this part v, we know, you guys alright? Alright, we know this is just going to be u v prime plus v u prime. And so we've got x v prime, and it's probably a good idea just to write down u prime therefore equals 1, v prime will give you 2y dy over dx. And therefore u v prime would just be x times v prime, which will be 2y dy over dx, plus v, which is y squared, times u prime, which is just 1. And therefore we've differentiated this using the product rule, like so. Is that okay? Alright, let's now apply that to a more concrete example. Are we on example 3? What is this, example 3? Okay, so given y squared plus 3xy plus x cubed, let's make that clear, x cubed equals 25. The question is, find dy of dx in terms of x and y. I'll give you a minute to have a little go, and then we'll go over it. Sorry? X and y. In terms of x and y. There you go. In terms of x and y. Hands up if you're done. Okay. What did you get? Excellent. Okay. As you done? Okay. All right. I'll just write out the solution. Hands up if you're stuck. You want to go over it? All right. Just bear with me. Okay, hands if you got that? Okay, brilliant. Any questions? Okay, alright, last but not least, now let's look at an algebra question. It's quite nice. This is a really good one. And let me write it out like so. So say you've got y equals 1 plus x, 1 take away 2x all cubed, divided by 1 plus x squared square root. From what we know so far, how would you differentiate this? Quotient? Product, chain, quotient, the whole thing together. Any other suggestions?
Find y.
Find y?
Find dx by dy.
Okay, so flip it the other way around. It's still a pretty nasty little thing where you've got product, quotient, chain, all of that involved. Edera, any suggestions about what we can do here? Alright, so Usman, so this example is quite an important one because it's quite a heavy loaded question actually. And you can imagine if you were to use all three rules, it's going to be quite some working out. But luckily, we can do things using implicit differentiation. And what that means is, in a question like this, we can simplify it. And this is how you do it. What you do is start by taking the logs of both sides. So if I took the log of both sides, what I'll get, in fact, if I can just write it out like this, so I'm going to take the ln of both sides, and I'll just put a square bracket around that. So that's essentially what I've done, just taking the ln of both sides. And then I can invoke the multiplication, division, power rule. So I've got ln 1 plus x plus ln 1 minus 2x cubed minus ln 1 plus x squared square root. And I'll emphasize that this is a minus sign. Okay, and here then you've got a plus. And then using the power law, we can just tidy up the powers. So you've got ln 1 plus x. Don't forget the bracket, otherwise it can be misleading. 3 ln 1 minus 2x minus a half ln 1 plus x squared. Now we can differentiate implicitly. If we differentiate both sides with respect to x, Ella, what would you get for ln y? Excellent. 1 over y dy over dx. Asim, what would you get for ln 1 plus x?
1 over 1 plus x.
Excellent. Matthew, what would you get for this one here? It's a bit of a
Which one?
3 ln 1 minus 2x. Yeah.
Get 3 over 1 minus 2.
Okay. 3.
Oh no, times 2.
Excellent.
Times minus 2.
Yeah, times by minus 2. Excellent.
Minus 6.
Yeah. Okay. So don't forget that part. That's where basically you're doing the chain rule. Maybe I shouldn't write times so big. I'll put down.
Minus 6.
Yeah, I'll put down just so people can see where the minus 6 has come from. I'll put that down as that. And essentially what we've done is done the chain rule, and you can write that out step by step if you want. Ln of u, and then dy over du times du over dx. dy over du is going to give you 1 over u. du over dx is going to give you minus 2. So it's minus 2 times 1 over u. And then finally, Anna, what would you get for the last one?
Minus 2x over a half.
Excellent. 1 plus x squared. And we can see straight away we can cancel those 2's out. Okay, so let's cancel those out. And that minus 3 over 2, minus 3 times minus 2 becomes a minus 6. And so we can write this out as y, so therefore dy over dx equals y times 1 over x minus 6 over 1 take away 2x minus x over 1 plus x squared. Okay. Because the 3 times the 2 gives us a minus. Yeah? Oh, so plus 1. Okay, happy? Alright. And given, now we need to just go back to the question. Obviously, I've just said to differentiate this, but if you want it in terms of x's, we know what y equals to. Y was just equal to 1 plus x 1 take away 2x cubed divided by 1 plus x squared square root. So this y is just this part here, and then times by what we've got inside the bracket, so x plus 1 minus 6 over 1 take away 2x minus x over 1 plus x squared. And that's it. We're done. Any questions?
Sorry, did you just say this is the short version?
Yeah, I said this would save you, once you know how to do this, so you've done a couple of them. But what I'll suggest is, if you want to try it out, try it the other way as well. The quotient, remember, is made up of the v squared at the bottom, v u prime, u v prime, and maybe then to do the numerator, then apply the product rule. So there's quite a bit to do. But once you can see what's going on, you can probably just do this in 2 or 3 lines. Yeah.
Why are you able to do it with the logs?
Okay, good question. The reason is, if you look at this carefully, okay, what you've got involved is a multiplication, a power, and a division. Okay, and the logs allows us to convert those into addition, subtraction, and the power law just brings the power down. And so therefore, think about it. Pretend that was to the power 30, right? And you're trying to expand that out or trying to use it. So by using the logs, you can simplify the whole thing. Turn the multiplication to a plus, a division into a subtraction, and then bring the power down. So it essentially simplifies the whole situation. Yeah? Okay, any other questions? All right, great.